Which of the following statements about sn1 and sn2 reactions is true? Let's take a look at all of them. sn1 reactions are favored in polar aprotic solvents. This is actually incorrect. sn1 prefers polar protic, whereas sn2 prefers polar aprotic. Now, sn1 can still occur in polar aprotic conditions and vice versa, but we're talking about preferred, like favored, okay? So it would rather be in polar protic solvent conditions. Now, the reason is sn1 involves carbocation intermediates, right? This is our leaving group, it's bromine. And the thing is, a protic solvent can be something like this, right? Like methanol. This OH can cause like an ion dipole type of interaction between the carbocation and also the leaving group. And when it does that, it like stabilizes it in a way. And when the carbocation is stable, that means that's easily reachable, meaning that it takes lower energy. And the carbocation formation is our rate determining step. And if it takes low energy to reach that, it's going to make it go faster. So that's kind of like the reason. Now, the thing about SN2, why we don't want polar protic, like this is an example of a polar aprotic solvent. This is like THF, tetrahydrofuran. The thing about SN2, right, is that it does not involve a carbocation intermediate. It's like a one-step thing. So like let's say you have your nucleophile. If you have a protic solvent like this methanol again, it would interact with this nucleophile and kind of hinder it and prevent it from even reacting. So it rather would have an aprotic solvent that doesn't have those type of ion dipole interactions with the nucleophile. So once again, A is going to be incorrect. Now for B, SN2 reactions proceed with inversion of stereochemistry. This is actually true, and the reason is that for SN2 in particular, we have something called a backside attack, right? So this nucleophile will literally come from the back, kick this bromine off, and now we can have this, okay? And so like this type of thing is called inversion of stereochemistry because we went from a wedge to a dash. So B is good. Now C, SN1 requires a strong nucleophile. This is not necessarily true because the rate law of SN1 is going to be K times substrate. That's all it is, okay? There's no nucleophile or anything in the rate law. And the reason is this is because the rate determining step, as mentioned before, is the formation of the carbocation intermediate. So regardless of the nucleophile, it's not going to matter. All we focus on is the carbocation formation. If that goes fast, then the rate will be fast overall. If this goes slow, then this will be slow type. You know what I'm saying? But SN2, on the other hand, is going to be K times substrate and nucleophile. So you actually want a good, strong nucleophile to increase the rate of SN2. But we're talking about SN1, so we don't need a strong nucleophile, so this is incorrect. Now, the last one, SN2 reactions involve a carbocation intermediate. We already determined that SN1 is what involves this. But once again, the reason why we don't have a carbocation intermediate is because it's all a one-step process, right? It attacks this carbon and kicks out the leaving group in one step. So D is incorrect, leaving us, which is B.